Hi, everybody. This is Tony DeLegio with Plastics Technology Magazine, and I'd like to welcome you to today's webinar, How AI is Revolutionizing Resin Conveying. This webinar was made possible by our sponsor, Conair, and in it, we will discuss how Conair's patented Conveying with Optimizer system utilizes AI, or artificial intelligence, to overcome resin conveying issues automatically. Specifically, we'll discuss what the system includes, its benefits, the problems it can overcome, and how processors can upgrade their systems. Today's event is an interactive one, so if at any point during the presentation you have a question, please type it into the webinar interface, and we will address it during the Q&A session that follows. Also, please note that everyone who registered for today's webinar will be emailed a link to a recording of it, so you can review it again at your leisure. That recording will be posted under webinars on the events tab at Plastics Technology's website as well, ptonline.com. Today's presenter is Justin Carter, the Conveying Product Manager at Conair. Justin has been with Conair since March 2016, primarily working as a project manager in both material handling and heat transfer systems. Currently, Justin has been tasked with being Conair's definitive expert for the conveying product line and leading that flagship technology. Justin has a bachelor's degree in secondary education mathematics. With that, I will hand it over to Justin and we'll get started.
Thank you. So thanks everybody for joining today. Um, we want to go through a product that really everybody here at Conair is incredibly excited for because of what it's going to do for people. So that product is called Conveying with Optimizer, and it's driven by our AI technology that we have embedded into our smart FLX. So let's jump into what is Conveying with Optimizer and what does that do for operators. So Conveying with Optimizer is a proprietary system that we came up with. It continuously monitors everything that's going on in the conveying system, so it changes or sees when something changes, and it's looking at those changes in real time, and it's going to react in real time to maintain the performance of the system and continuously tune, continuously optimize what's going on. Why would we use Conveying with Optimizer? Well, there's a bunch of problems that Conveying with Optimizer is going to help us out with. So first of all, we have our smart FLX, which we have this AI technology embedded into. And because we're continuously monitoring the conditions in the conveying system, we're going to now use that technology to automatically react and really eliminate the manual airflow adjustments. So a couple of the pictures that we have on the screen here, I think everybody is familiar with some variation of what we have on the top, which is a manual distribution box. So I'm showing our version here, which has a tube within a tube design. You see the hand that is adjusting our airflow ratio. It's going to pull the tube out to let more material in, a little bit less air, or push it in to close off the material so you're pulling more air. Those can be a big hassle at some plants. They're either several hundred feet away, or it's raining, snowing outside, nobody wants to go in. You've got silos that people keep the doors locked, so you got to remember where the key's at. It can be a hassle to always make sure that that adjustment is in the correct location. Not to mention, you have to understand what that change does to the system, and you've got to try to keep people from just going up and messing with it without understanding what they're doing to the system. Conveying with Optimizer takes that away, so we're automating that. There's nothing manual for people to change when we put this system into effect. So what problems does it solve? There's so many different dynamics within a conveying system. So, ultimately we're trying to move as much material as we can. We're trying to move it at the right speed, so we're not degrading it or causing, wear on the material lines. But there's always things changing. From over time, the filter's getting dirty. You've got lines that wear, so maybe you got a small hole in an elbow that's letting in air. you've got coupling leaks because the gasket just gets brittle over time. We've got customers all over the place. So some places see big humidity swings in the summer, especially, where that humidity now makes your material really wet, really heavy. If you're processing a regrind, the shape and the density of that regrind changes depending on, you know, the condition of your screen, how sharp your blades are. And then if you're running through any sort of a common line or a manifold system, your distance from the pickup point of the material to the machine receiver can be severely different from one source to the next. It's a little bit more about vacuum leaks in the system. So this isn't something that is typically you know, I guess a big all at once type of leak. These come on slowly. So, I mentioned how the gaskets on the couplings get brittle. That just takes time. They get, I guess, kind of hardened, brittle, and then over time they start to crack. You get a little bit more air in, and it just builds and builds and builds. And all of a sudden you notice, hey, I'm not getting as much material here as what I was trying to. So that, starving of the machine can result in, bad parts, can result in just not having enough to run your machine. So we want to make sure that we're always seeing that and adjusting it in real time so that we keep that vacuum pressure where we want it. Clogged filters, I think this is something that every plant sees at some point. It's as you're running material, you're always generating dust. That dust, whether it's in a dust collector filter, kind of like what we're showing here, or whether it's in the filter that's at the receiver, you're always having to go through and either swap the filter out or clean the filter. But when you put in a new filter and it's perfectly clean versus when that filter's been in for a couple months and it's starting to get clogged up, all of that affects how your conveying system is performing. So we could waste energy as the pump has to run longer to move the same amount of material versus if we are able to kind of optimize that system and make sure that we're moving material consistently from pole to pole. This one I think isn't something that's always at the top of people's minds, but as I'm kind of showing in the picture here, humidity can be a big impact on the system. So, you know, the silo has a massive puddle of water under it. I'm sure a lot of people on this have opened the door to a silo and it feels like you're walking into a rainforest because there's just water running and dripping, or you've got a puddle under the distribution box. So as that humidity changes, materials can either absorb the water or just you have that surface moisture. All of that changes how heavy the material is, and really, with that, how much effort it takes to move the material. So, again, we're seeing how all of that changes the pressure in the system, and we're adjusting continuously to keep us running optimally. Not all material types are the same. So, we have a couple different variations here, from a virgin pellet to a long glass fiber to a regrind sample. As you change from one to another, each of these has different properties. Some are easier to pick up, some take more effort to pick up, some are heavier than others. The geometry of the pellet or the material impacts how easy it is to convey. So switching from one to the next may not seem like a big deal. Maybe your bulk densities are the same, but all of those different variations in combination with everything else that we've mentioned can really impact the performance of the system. And then this one I mentioned a little bit with common line systems or a resin selection station, cam lock stations, but you could be pulling from a source that maybe it's a surge bin right beside your selection station one day, and then you go to run a different product and now your silo's an additional 200 feet away. Or you've got a common line system and you've got 8 machines hooked up to this common line system. One of them is 100 feet from your pickup point, and the next one is 300 feet from your pickup point. Well, 100 feet of conveying is a lot different from 300 feet. So what our system can do is it sees that difference in pressure, and it can maintain an individualized recipe for each receiver based on the source that it's conveying from. How does this affect our pump? So one of the best parts about this technology is that we can really use this for any vacuum pump. Ideally, that's a Conair pump, but we can do it with competitive pumps. But unlike some of our other products like Wave, we don't need to use a specific high vacuum blower to move the material a specific way. We can use those, but it's not required. Really, all we need here is to monitor the pressure at the pump, and that can be just a very simple retrofit of adding a transducer underneath a manual gauge like what we're showing here. But by continuously monitoring, continuously adjusting the system, we maintain a more stable flow of material. And if you saw the demo of what we're doing, with this at NPE, what we were able to do was kind of mimic some of these issues with conveying at our stand. And because of how quickly this system reacts, we're able to really, I guess, eliminate the problems before they formed. So there were a couple days where I had big slugs of material that moved through the line. In a lot of plants, that would have caused a clog. That would have caused somebody to have to go through tapping to see where the clog was, disassemble lines. I mean, you could be talking hours, if not days, of troubleshooting, but we addressed it before it turned into a bigger problem. What that means is that our pump is running more efficiently. So we're getting better pump utilization because we're constantly tuning the system versus a static adjustment, and then you go and you mess with it when you notice the problem. We fix the problem before an operator even notices. So let's get into a little bit more about how this works. There's really 3 main components here. One is the optimizer valve itself, which we're showing on the screen here. The second is what I just showed a second ago with a pressure transducer. And then the brains of it, what really makes this all function, is our smart FLX control. So we do a lot with our smart FLX. It's a basic conveying control. We've got items like the optimizer, which we're showing here. We can do selection stations like our RSS with RFID or the auto RSS. If you've seen our wave conveying, we run all of that through the smart FLX. So it's really versatile, and in this case, it's 100% the brain of what we're doing. So this optimizer valve replaces manual feed tube adjustments. So you're not having to go out to the silo or go over to a surge bin, adjust the pickup, listen for how the material is moving through the line, maybe go to your pump, check what the pressure is on the pump, and you're running back and forth to try to get it tuned in the way you want. This replaces that. It does all of that for you. So the valve and the pressure transducer can be easily retrofitted into most systems. I kind of hit on that one already, but we don't need specific pumps. We don't even need our pumps necessarily. We basically need these 3 components here, and we can make it work in the system. So how does it work? We show an image of our smart FLX control here, and we've really got 2 modes that we can run this in. One is the automatic mode, which is really where I think most people are going to want to run this. The second is manual mode, where you can, I guess, set a fixed position of what that airflow at the pickup point is going to be, and that would be similar to your manual adjustment on the feed tube itself. In automatic mode, you're giving this a pressure set point, you're giving it a high band and a low band, and that'll give you a visual indicator on the screen of kind of your tolerance. So what this is going to do is it's going to always try to hone in on that pressure set point, but you're going to have this range of where your acceptable pressure fluctuation is. So it's going to adjust a lot quicker when it's outside that band, and then once it's inside that band, it starts to slow down and hone in on what it's actually trying to do. It continuously adjusts to reach our set point. So that's kind of what I mentioned just a second ago, where it if it drops way down, and let's say my set point's at 9 inches of mercury and it's seeing 6, it's going to take a fairly aggressive approach at trying to hone in on that 9. But once it's getting inside that green band, it's going to start slowing down to make sure it doesn't overshoot by too much. If you have multiple receivers that are hooked up to a single source, so let's say it's a common line system or a manifold system, and I have 3 receivers that are all pulling from a single silo, it knows that machine 1 and machine 3 are at different distances from that silo. So it's going to remember independent settings for each of those receivers. And on the Smart FLX, we can constantly monitor what the actual pressure in real time is and what the valve position is. One of the questions that I got the most at NPE when looking at this is, how can we use this as a diagnostic tool? And I think how I answered that to most people was, there's a lot of things that can purposely affect the pressure in the system. So I ran a different material. I pulled from a different source. Those are things that you're doing intentionally that adjust or change what that pressure is. But there's also things like leaks, dirty filters that are happening that are definitely not intentional. So if we look at that valve position, in most plants, that valve position should not change on a day-to-day basis. Maybe little adjustments here or there, but it's going to be pretty well set. If your valve position is at 85% one day and 70% the next day, there was a big change that maybe you weren't aware of. Our valve is adjusting to compensate, to make sure that you're still in production, you're still making parts, but that tells you that there's a bigger problem that you probably need to start looking for to address before our valve can't ultimately adjust for it. What we try to do is we want our valve to adjust from basically end to end in its spectrum of adjustments before it really throws up an alarm and says, I've done everything I can do. Now there's a bigger problem that we need to address. But by monitoring that valve position, we can see what's changing and know whether it's a change that we made to the system, like running a different material, or whether it's something that we didn't know was happening in the first place. So a little bit more about the options and what all we can do with the setup of this. We've got a variety of valve sizes, so anywhere from 1.5 inch up to 4 inch. And then we can mount these remote or inline. So the picture on the screen is going to show an inline mounting. It's exactly what it sounds like, where we've got our valve on a T, and that valve is put right in front of our pickup point, within about 5 feet or closer of the pickup point. But let's say I have a silo that's way out in the middle of nowhere. I don't have a control panel over there. I don't want to put a control panel over there. So I need to I need to find some way to locate that valve closer to the control while still pulling that material with Optimizer. So we can remote mount these where we cap off one end, the other end plumb almost like a Venturi effect to the front of the silo, basically in the same position that that valve is located now. And now that valve can be put in a more accessible location. So we'll recap a little bit about what this system does and what the advantages are. So to start with, it's completely retrofittable. So the biggest, I guess, requirement for most people is having the smart FLX system. If you already have a smart FLX system, it could be as simple as a software upgrade. So, that is really the biggest thing to take into account. The pumps, we can work with our pumps, we can work with any existing pump that's in the system, and then we need the optimizer valve. Just to give an example to most people, the optimizer valves are very, very minimal cost. So where some purge valves and you know I guess other devices might be a couple $1,000s, our list price on the optimizer valve is $1,500. Very minimal upfront investment. We maximize the productivity by continuously changing, continuously tuning the system so that we're not having people always, you know, go through and adjust to get a little bit more. Maybe I'm moving the material too fast, so I need to slow it down a little bit. It really takes the user interaction, and now they can focus on other things. And with that, I'll wrap up and we'll get to any questions that there are.
Excellent, great, thank you, Justin. As as Justin mentioned, we're now into the Q&A portion. So if you have any questions for him, you can type those into your interface. We already have a few, so we'll dive into those. First off, what vacuum pumps will work with conveying with Optimizer?
So really any vacuum pump. Like I said, that could be ours, that could be a competitive pump. The biggest thing is we need some sort of a threaded coupling to add this pressure transducer. As long as we can work that in, we can work with any pump.
Excellent. So we got some flexibility there.
hmm
Will conveying with Optimizer work with other non-Conair conveying systems and controls?
So not with conveying controls from other vendors. It has to be with our smart FLX system. So the valve is obviously a portion of that, and that's the mechanical side to how we're making this work, but the brains of this is really in our smart FLX control.
Gotcha. Okay, so that's a key element. Um, in terms of resins and materials, are there any types of resins or materials that the conveying with Optimizer does not work well with?
Nothing that we've found yet. So, I mean, it can work anywhere from regrinds, virgin pellets, all the way up to powders. You know, where our wave technology in the past had, I guess, some areas where it was more beneficial than others. Highly abrasive materials where we could slow the material down and really limit the wear on the piping, or incredibly soft materials where we can again slow it down and protect the material itself. This works in a wider range of dilute phase conveying.
Okay, so we can cover more material types and densities.
hmm
Okay, with does conveying with Optimizer use the data it collects to make more optimal adjustments over time? For instance, is it learning from data it collects on my conveying setup over time to make improved adjustments?
Absolutely. So it's remembering from material pull to material pull every load cycle. It's remembering what it did on the last cycle and adjusting upon that for the next cycle, and then it can maintain individual recipes for each receiver based on the source.
Gotcha. Okay. So we've got a working memory. Um, let's see. Can the conveying with optimizer be retrofitted onto existing conveying systems?
Yeah, so it can be retrofitted in. I've hit on this one a number of times. If it has the smart FLX control, then it's a very easy retrofit. If there's a different control system, then we need to add the smart FLX in. But other than that, it's a very easy retrofit. We're adding a transducer. We're putting this valve essentially in, replacing any feed tube adjustment or pickup point adjustment, and you know after we do that, we're off and running.
Okay. Excellent. You had mentioned the wave conveying system that you guys had put out earlier, and this individual was wondering, how does this system compare to wave conveying? What are the differences?
Yeah, so wave conveying is very powerful for, I think, specific applications. So if we have glass filled materials, something that's heavily abrasive, we're able to really protect the piping, minimize pipe wear by slowing it down. Or very, very soft materials that create angel hair or high amounts of dust as it's being conveyed, we can control the speed with a VFD on the vacuum pump, and we're constantly controlling the airflow at the pick-up point. We can create slugs of material moving through the line. So there's absolutely applications where wave conveying is the better solution. But there's also a higher cost to entry with wave conveying because we need these deep vacuum pumps like our LDP or HRG vacuum pumps. Whereas with Wave, we can touch, or with Optimizer, we can touch a broader range of applications because we're not pushed into specific vacuum pumps. It is dilute phase conveying, and it's only dilute phase conveying, but you can adjust kind of the thickness of the material flow by your pressure adjustment.
Okay. Have some more questions coming in and want to encourage folks to keep typing those out. Can this optimizer detect clogs in real time in the conveying line?
So it can, because it will see the pressure, but I mean, ideally, we're going to clear that clog before the clog even forms. I made a couple references to the demo that we were running at NPE, and we were able to both simulate a leak in the system, simulate a dirty filter. We were doing this very quickly, sometimes within a load cycle. So you know, if I would have a leak in the system and then I would take that leak away in the middle of the load cycle, I would send a slug of material moving through the line. Normally, that would be something that would clog a normal conveying system. But because we're seeing what the real time conditions are and reacting, we're able to get more air in the line and push that slug through and then get ourselves back to a normal conveying flow.
Okay. So it can obviously detect it, but the goal is to just avoid them in the first place.
Correct.
Gotcha. Excuse me. Um, can you mimic dense phase conveying with this setup?
Not really mimic dense phase conveying, so this is going to be purely dilute phase. You can, by adjusting the pressure and what that pressure set point is, you can thicken up the material flow a little bit in the line, but it is still going to be a dilute phase system. Um, how how dense you can make that material is going to be a function of what vacuum pump you're using. So traditional positive displacement pumps have a relief valve that's set somewhere around 12 inches of mercury. So most plants will run them at maybe 8 to 10 inches. If you go with a higher vacuum pump, you can then increase that pressure and get a little bit more material in the line, but it's still going to stay within that dilute phase realm.
Gotcha. Does this system integrate into Conair Smart Services, or is that the same thing as Smart Fix?
So it can integrate into smart services through the smart FLX. So smart services is our industry 4.0 solution. Every smart FLX that we make goes out smart services ready. So if you add smart services, you now get a web enabled look at what we're doing through the smart FLX. Maybe it's through blenders, maybe it's through dryers. You can see any of those devices that are connected to the smart services system, and you've now got basically a remote machine control as well. So absolutely adding smart services is a great way to monitor this system and additional equipment.
Excellent. Will I get an alarm when my vacuum pressure changes?
No, not at this time. That's always something that we're going to do, I guess, pay more attention to as we develop this system. At this point, it will not alarm until the valve can't adjust anymore. And the reason we've done that is that we don't want to throw up nuisance alarms. So if I go to run a different material or if I go to run from a different source, that could impact the pressure. And I don't want to just say, well, my pressure changed. Here's an alarm. Somebody take a look at this. Some of those changes are done intentionally. So, we know what changed within the system. What we want to do is make this system address those changes and adjust accordingly, but we only want to throw up an alarm when this the system basically can't keep up. I can't adjust to keep within my operating parameters.
Gotcha. Okay. And then that does make sense where you wouldn't want just everyday changes to trip something. And a question here, does the smart FLX remember recipes and materials with the inline pressure induced? But I guess maybe kind of makes sense of this. Um, I guess when it's remembering the recipes for certain materials, is it remembering some of the pressures that were experienced as it conveyed that and kind of creates a baseline for that material from that source? Or what, I guess, what is it remembering, or what can you store in a recipe?
So it remembers what the valve position was and where its pressure was. So if, let's say, at the end of a cycle, my valve position was at 65% and I was still well above what my pressure set point was, it knows that I need to now induce a little bit more air into the line to bring that pressure down. So it knows which direction it needs to adjust, either open or closed.
Okay, that makes sense. I guess in general, we talked a little bit about the convenience of the system and not having to manually go and make these changes, which saves time, but also over that time, you're conceivably maybe using more energy than you needed to. Or do you guys feel that over time, I mean, it might be case by case basis, but that users of this system would also benefit from some energy savings over time?
Yeah, so there's different obviously thoughts and philosophies on this with variable frequency drives and running at a slower speed, or this there's no VFD needed. So our thought here is that by making sure we're loading as efficiently as possible and we're keeping our load times as short as possible, that pump is going to basically be working effectively every time it goes to move material. And with that, it can get more idle time now and it can stop when it's not needed. So a good example of this would be at the show. We were running, I believe it was a 60-second load time on our demo. I induced a vacuum leak in the system. My load time on the next cycle shot up to about 72 seconds. So I lost 12 seconds to move the same amount of material because we had a fill sensor in our receiver. So we were always filling to a common point. Within about 2 load cycles, I was already back down to my 60-second load time because the system was able to catch up that quickly.
Making those adjustments. A question here, kind of a hypothetical. If I have 15 receivers on my smart FLX, Can I add optimizer to some of my receivers, but not all?
Yeah, absolutely. I mean, it's more a function of what source they're pulling from. So, let's say uh, three of those receivers are pulling from a silo, and maybe that silo is a longer distance away, or it's got a difficult material to convey, and we want to make sure we keep that setting kind of, I guess, narrowed down pretty tight. We could add it to that line, and the other 12 receivers on that smart FLX could just run the way they normally do.
Yeah, kind of along the lines of that question, as you guys look at quoting out new systems, I mean, do you feel like from Conair's standpoint, this would potentially change how you'd lay out a system? What equipment you would include? Have you had any new case scenarios with a customer applying this where you maybe it's kind of changed your conventional thought process on how you lay out a plant-wide system?
Yeah, I mean, we're definitely taking a look at it as far as, there's there's cases where it's more advantageous than others. So, if I have a blender that's sitting, press side, and it's conveying, 20 feet into the machine receiver, that's probably not a case where we need something like this. But, when we are coming from silos, or we've got selection stations, cam locks, you know, those can be areas that require a lot of attention, a lot of adjustment to make sure they're running efficiently at all times. So those are the areas where it's a lot more advantageous to put something like this in.
Gotcha. Yeah. Um, do the abrupt changes in pressure induced by the valve have any side effects on the health of the pump or the conveying line?
No, so they're in a real time situation, these changes are, minuscule compared to somebody going and opening and closing a distribution box. It's just a kind of a, I guess, a constant tweaking to the system to make sure that it's optimized. It's not like we're taking a valve 100% open and closing it 100% at the snap of a finger. So, we're not generally seeing a pump spike to 12 inches mercury and your relief valve is chirping. We're just making steady adjustments to kind of keep it where it needs to be.
Gotcha. Yeah. And in terms of that, I mean, do you see, have you guys done any tests to look at like the overall quality of the material as it's conveyed, like the health of the material in terms of, stringers or fines, or if you had other systems maybe where you guys are making minimal adjustments over time and kind of keeping a good flow. Have you looked at, I guess, like the health of the conveyed material? Does it come out in better shape with a system like this?
We did that more when we were implementing wave conveying than we've done with this. So what we've seen with this system is, because we know that we're running material the way we want to in a dilute phase, that it will have a modest impact on that. But if angel hair or dust is a heavy concern, then that's where something like wave conveying is probably more advantageous.
Gotcha. Okay. Excellent. Well, I am looking through the questions. It appears that we have gotten through all of them. I want to thank Justin for an excellent presentation on a exciting new technology, and also thank Conair for making today's event possible. I'd also want to thank all of our attendees for spending some time with us this afternoon and learning some things. I know I did. I hope you did as well. I'll remind everybody that if you had registered for this webinar, you will be emailed a link to a recording of it, so you can view that again at your leisure. And you can also find that recording at the PT website on the webinars section under the events tab. So with that, again, I'd like to thank Justin and Conair and all of our attendees. And I hope you all have a great rest of your day, and join us again in the future to learn some more, hopefully. So thank you very much.